of that topic. This lecture assumes that you know what pointer is, what arrays are, and it continues on that, right? It continues the rest of the topic. The first thing I decided to do at the beginning of this lecture is to remind you of how the process address space looks like in Unix operating system. So when you create a C program and you run it, the program, which becomes a process, will use memory in an organized fashion. This is how the process address space look like. In other words, this is how a process use the main memory. It breaks it into separate pieces. Each piece or each section is called a different section. This lowest section, which is in the lowest address, is called the text section, which is going to store all the CPU instructions for your program. This is basically your program after being compiled by the compiler. Then after that, we have the data section, which can be broken into two pieces. One is the initialized data, one is the uninitialized data. In the data section, we store global variables. For example, if you have an initialized global variable x equal to 0, you store it here. But if you have a global variable y with no initialization, you store it here. That's not the golden standard. That's basically the Unix standard to store, to manage the address space of a process. And then after that, we have two more sections. We have the stack section, we have the heap section. I talked about the stack a lot. It stores each function's local variables, starting with the main, which is going to be stored on the top of a stack. The top of this shape is showing you the bottom of a stack. So that's basically the first thing that you put in the stack. Anytime that you call a new function, you push another block into the stack. So a stack grows downward. And then when a function returns, we pop that block for that function from the stack. So the stack memory allocation happens automatically. When a function is called, we allocate some space for the function and inside the stack. And the stack memory deallocation happens automatically when a function returns. When a function returns, we don't need its local variables anymore. That's why we pop that block associated to the function from the stack. So the stack will free its memory automatically and it allocates memory automatically. When a function is called, we allocate memory for the stack. When a function returns, we deallocate memory from the stack. So the stack memory management happens automatically. The only remaining section would be heap, which you see it right here. Heap is similar to a stack in the sense that the size of heap grows and shrinks dynamically. So we don't have a fixed size for heap and stack. For data section, the size was fixed. For text section, the size was fixed. But the heap can grow and shrink. However, the heap is not going to be automatically managed. Who's in charge of managing heap? The programmer. The programmer can dynamically allocate memory and it can deallocate memory or free the memory using the free function. I'm going to go through how heap is managed today by showing you some basic implementation of heap alloc and free function, and then showing you the standard versions of malloc and free function. And then I'll talk about some other versions of malloc, which is called calloc and realloc, and then, help you understand things better. Let's continue. The next thing I wanted to mention is, before I show you the standard versions of malloc and free, which is used by programmer to allocate memory in the heap and deallocate memory in the heap, I want to show you a rudimentary storage allocator using pointers that is designed by the author of the textbook. It's a very naive version of it. It's not even close to the real malloc and free, but it helps you understand it. The author of the book decided to implement its own memory allocation and free function in the form of a stack. It's called alloc buff. Remember, heap is not going to be a stack. Heap is much more complicated than a stack, but this is the rudimentary version just to teach you how it operates and just to teach you how real malloc and free can handle the heap. Imagine this alloc buff is a long array of bytes that is depicted here. So this is basically your heap. And we are going to handle the heap in the form of a stack. You know what a stack means? That means last in, first out. Is this how we handle the heap? No. The real heap is not last in, first out, but this is a basic implementation. Just like any other stack, we need to keep track of the head of the stack, or the top of the stack, I should call it. We call this alloc p. Alloc p is a pointer pointing to the top of the stack, right? This is the stack bottom. So let's call this bottom of the stack. And this is the top, right? This memory is already allocated and the rest of it is free. So anything other than that is the free part of the heap, right? But we're gonna manage the heap in the stack fashion, which is last in, first out. When you're allocating some block or some amount of memory, you basically have to push it to this stack. And when you're deallocating, you're popping it from the stack. To allocate memory, we use this function called alloc, which is basically the basic version of malloc. And when we are freeing memory, we use free, which is a basic or rudimentary version of the real free function that we use for the following assignments and the rest of the class. So in other words, alloc is going to push something to this stack, and free is going to pop that block from the stack. And that's how you allocate memory and deallocate or free memory from the stack. The call to free should be in the opposite order of the call to the alloc function. The reason is obvious for those of you who have used the stacks before. You know that if I push 5 elements, 1, 2, 3, 4, 5, the pop will pop them in the opposite order. So if I push 1, 2, 3, 4, 5, pop will pop 5 before 4, and 4 is pop before 3, 3 is pop before 2, and 2 is pop before 1. So that's why the calls to free must be in the opposite order of call to alloc. That's because we use stack, which is a last in, first out data structure for this rudimentary version. But in the real version, the order doesn't matter. You can free in any order you want. So if I allocate 3 blocks in the order of 1, 2, 3, I can free any of those 3 in any order I want. I can first free 1, then 2, then 3, or I can free 3 before 2, before 1. But in this version, we have some limitations because we are going to create a very basic version. This is the code for alloc. Even the basic version looks complicated, right? And this is the code for the free version. the A free, yeah, the free basic version of free. How do you implement alloc? Alloc is a function that gets the number of bytes that you want to store or you want to allocate, and it returns a pointer to the allocated block with the type char star. Why do we use char star? Because char is a data type with 1 byte, and we are going to basically allocate blocks of a number of bytes. So the book decided to use char star as the return value. It doesn't really matter what the return value is in this example. How does alloc works? Basically, we start with the alloc buff, which is the name of that stack. That's the pointer to the beginning of the stack, plus alloc size. That's the capacity of your heap. You don't have more memory than alloc size, which is set to 10K. That means, you have only 10 kilobyte of memory. And then I do minus alloc p. Alloc p is the pointer to the first free cell. If this is greater than or equal to n, that means you have more than n free bytes. Let me tell you what this if means in a different way. Alloc buff is head of the stack or at the beginning of the stack. This is the size of the stack or the capacity of the I shouldn't call it a stack, I should call it heap, but we are designing it like a stack. But this is the beginning of the heap, this is the size of the heap. When you add these together, you will get the very end of the heap. This is a char star, the alloc buff, and this is the number of bytes in the heap. When you add a pointer by a number, if you remember about pointer arithmetic from the last lecture, this is going to give me a pointer to the very end of the heap. If I subtract this pointer, which is going to point to the beginning of the free section, from the end of the heap, that's going to give me the amount of free memory. Let me tell you in this picture. So alloc buff is the beginning of the heap. When you add it by alloc size, you get the pointer to the end. I call it the end pointer or NP. And if you remember, alloc p was pointing to the beginning of the free section. So let's say these are all occupied, and alloc p is pointing to the free section. When I subtract alloc p from NP, which is basically equal to alloc buff plus alloc size, that's going to give me the number of bytes that I have, and it's free. The rest of it is occupied. If the amount of free memory is greater than what you're allocating or what you want to allocate, which is n, then we are going to do the allocation. Otherwise, we're going to return 0. You return 0 or null. This is basically the null pointer. You return null when you don't have enough memory. That's exactly how malloc works. Malloc is the more complicated version of this, which returns null when you don't have enough space. But if you have a space, then you need to place it here because it's a stack for this rudimentary version, and return a pointer to it. And at the same time, you need to update alloc p because the top of a stack is not here anymore. You should move the top of a stack to the end of the allocated space. So that's what this line does. It updates alloc p, it adds it by n, and it returns alloc p minus n. Why do you return alloc p minus n? When alloc p points to the end of this allocated space, alloc p minus n points to the beginning of it because the size of that allocated space is n. And you return that because this way you can pass this pointer to anyone who needs n bytes, and they can use n bytes for whatever reason. They can store n characters in it, or they can store n over 2 short integers, or they can store n over 4 regular integers in it, or they can store n over 8 long integers in it. They can store double in it. They can store a movie in it. They can store a picture in it. They can store it for whatever reason they want. Nobody cares. Just this is n bytes. I call it a char star, but they can store anything in it. They can store a character array or anything else. That's how the rudimentary version of malloc, which is called alloc, works. Let's see the chat. No, John, that's not true. The book decided to implement heap like a stack. Why? Because the real implementation of heap is a lot more complicated than this. You see, the alloc function is only 6 lines. The real malloc function implementation is super complicated. It's like 10 times or even 20 times more complicated than this. So that's why we don't want to talk about it. Right? But remember, the real heap is not managed by in the form of a stack. The real heap is managed in a different way. That's a totally different discussion. Okay. The rudimentary free up function is called afree, which basically gets a pointer to the beginning of the block that you want to deallocate, and it's going to free it. When you call alloc, when you call afree, you call alloc when you want to allocate some memory to do something with it, right? So let's say you need 20 bytes of memory. You call alloc with the input parameter 20, and then you do your operation with those 20 bytes. When you finish working with those 20 bytes and you don't need that 20 byte anymore, you want to get rid of it, then you free that to storage. Why do you need to free it? So that anyone else who needs that space can use it. So do not leave the garbage without deallocating it. This is not Java that has a garbage collector. You as the programmer is responsible for collecting any garbage that remains. This is basically, cleanup operation. When you finish dealing with some storage, you want to free it, you call the afree in this example, or in the general sense, you should call the function free with no a in it. FREE is the real function that frees space. But this rudimentary version is going to pop this block, and that's how it frees it. How do you free that block? You basically say, let's set the alloc p, which is the top of the stack, equal to p. Basically, you move the top of a stack from the end of this block to the beginning of this block. And this way, the block is gone. The block will be popped from the stack. This condition assures that p is pointing to the right location. It should be greater than or equal to alloc buff, and it should be less than alloc buff plus alloc size. This basically assures that the pointer is inside the heap. You're not pointing to a location that is outside of the heap. That's like an error handling part. And that's pretty much it. That's the rudimentary versions. If you didn't understand anything about this and you say, oh, I didn't understand any of that, that's fine, because this is just the authors of the book code, and this is the attempt by the author of the book to implement a rudimentary version of malloc and free. So if you don't understand it, that's fine. We're gonna move forward and see the real deal. This is what you must understand, and if you don't understand it, you cannot write C code for the future assignments and for the future programs, and you will not understand most of the content of the book, or most of the content that we cover in this class. We will use malloc function for allocating memory in the heap, right? I showed you all the 4 sections. I said the data section, text section, stack, and heap are the 4 sections. If you want to use heap, you need to call malloc. For the other three, we have different ways to use them. But for the heap, you need to use malloc. There's no other way. We have some other variations of malloc, like calloc and realloc, which I'll cover later. But those are basically the variations of this. Malloc is the most important function to learn. How to use it? What should I include to use malloc? You need to include stdlib.h. That's the first thing. What does malloc do? It allocates memory block, just like the alloc function that I showed you in the previous slide. What's the signature of malloc? It returns a void star. It's called malloc, M-A-L-L-O-C, and the input parameter is size t size. Now you may say, wait a minute, what does size t mean? Size t is a data type that is similar to an unsigned integer. The exact implementation, this depends on different machines and different hardwares, but size t basically is an unsigned integer, right? That means you cannot have a negative number as a size, right? You can forget about size t and store and pass a regular integer to the malloc. For example, if you need 10 bytes, you simply say, I need 10. Set the size to 10. If you need 100 bytes, then set the size to 100. If you need 1,000, set the size to 1,000. Don't worry about the size t. Size t is a type that you can cast an integer to it. So just use a regular int. Don't worry about what size t means. The return value is a void star, which I told you before. It's the most generic type in C, and every type can be cast to void star. So it's good because you're returning a generic type. You can cast it to any type you want later. What's the input parameter? We only have one input parameter, size, which is the number of bytes that you want to allocate. What you need to understand here and remember is that the value that you pass is in bytes. So if you want one integer and an integer is 4 bytes, you need to pass 4, not 1. If you want to store a long integer, you need to pass 8, not 1. The measurement unit of size is byte. What's the return value? It returns a void pointer, which is a void star. And that's the pointer to the allocated space. So the return value of malloc is an address that is inside the heap. Okay, I told you what the heap is. So it basically points you to a location inside the heap, which is part of the memory of the process. This void pointer would be equal to null if the malloc fails. When does malloc fail? Malloc fails to allocate memory if there is not sufficient memory available. For example, if you're allocating a giant space, let's say 1 gigabyte, the operating system says, no, you cannot have that, and malloc returns null. Or if you already have allocated hundreds of megabytes and then you want to allocate more, then the operating system says, no, you cannot have more memory, right? And the malloc returns null, right? So don't be shocked if the malloc returns null. That's the indication that malloc is not successfully allocating memory for you. As I said, because the return value is void star, if you want to use that return value for storing an array of characters, you need to cast it to a char star. If you want to use it to store an array of integers, you need to cast it to an int star. If you want to use it to store an array of doubles, cast it to double star. Let's see an example. Let's say you want to allocate an array of 5 integers. I'm going to allocate a space for an array of 5 integers. I'll do it this way. I will say, let's do int star r. That's a pointer to an integer. And I set it equal to malloc of 5 times size of int. What does size of int mean? That basically means how many bytes we need for an integer, which is normally 4. And 5 times 4 is equal to 20. That means give me 20 bytes so I can store an array of 5 integers in it. This is going to store the array inside the heap. If I want to have an array of integers in the stack, I will replace this line with a simple int r5, and that's enough. That's going to give me a local variable of function main inside the stack with the same size, 20 bytes, and I have it in the stack. So this is going to make it inside the stack. If you want to have it inside the heap, then you need to call the malloc. If you want to have that array inside the data section, which is in the lower address compared to heap, and I showed you in the very first slide, you need to define this array of integers not inside the main, outside of the main. So right before lines 1 and 2, before you start the main function, you can use the same exact syntax. You can say int r5. And that way, the compiler will allocate 20 bytes in the data section and says, here is your array of 5 integers, have it there. So you can store it either in the data section, outside of the main, or you can have it in the stack, define it like an array of 5 integers this way. Or if you want to have it in the heap, then you have to do it this way. Now you know where to store what. If you want to store it in the heap, you need to use malloc. Otherwise, you have some other ways to store it some other places, in the data section or in the stack. Let's see another example. Let's say you want to allocate a space for the string hello world. How do you do this? That's a super common operation that you want to do. You want to allocate a space for a given string. First, you need to create a pointer. Why do we need a pointer? Because the pointer should keep track of the allocated space. If you don't have a pointer, then you can allocate memory with malloc, but the address to that allocated space will be gone. You won't have access to it. So you need to define a pointer, like in this case, char star string, and set it equal to the return value of malloc. Similar to the last example that I cast the malloc return value to an int star, I should cast the return value of malloc to a char star now. Why? Because I want to create a string. So I need to cast the malloc to a char star. Before, I wanted to create an array of 5 integers. So the cast should always be there because malloc originally returns a void star, and we don't want void star. We want either char star or int star or something else. Then, in order to find out how many elements you want or how many bytes you want to allocate, you need to first find out how many characters you need. The hello world has this many characters, strlen hello world. If you remember, strlen was a function in a string.h that returns how many characters are in the string. It does not count the \0 at the end. That's why I'm going to add this by 1. This summation of the strlen and 1 should be multiplied by the size of a single character, which is equal to 1, but I just wrote it here for you to understand, what's going on. So I want length of hello world plus 1 characters. So I will multiply the length of hello world plus 1 by size of a character, and I will pass the whole thing to the malloc. If you want to know the numerical value of this, that would be 12. So basically, you're allocating 12 bytes. 11 of the 12 bytes will be used to store the characters of hello world, and the 12th one would be the \0 at the end. How do I store hello world in the string? You just need to use strcpy. strcpy copies one string to another, so you say strcpy string, comma, hello world. That's going to copy the hello world into the string. It's that simple. Okay? That's how malloc works. Now, let's get to the more interesting part. Let's talk about, by the way, I have to keep track of time. Okay, let's talk about other versions of malloc. I'm going to talk about calloc now, which allocates an array in memory with elements initialized to 0. So calloc is a version of malloc that clears and allocates. Malloc only allocates memory, but calloc not only allocates memory in the heap, it initializes all of them to 0. Who uses calloc? Someone who cares about the memory leak or data leakage, or they don't want the data to be, they don't want their memory space in the heap to contain garbage values or random values, right? So you basically use calloc to clear everything to 0, right? The signature is a little bit different from malloc. If you remember, malloc returned the void star. Here we still return void star. Remember, malloc only gets a single input parameter called with type size t. That would be the number of bytes that you want to allocate. But calloc gets two parameters. One is the number of items you want. The other one is the size of each item. It is kind of similar to malloc. I'll tell you how it works. Let's say you want to write a program. That's an example of calloc. Let's say you want to write a program that uses calloc to allocate a space for 40 long integers. And you want to initialize all the elements to 0. That means every single long integer is initialized to 0. You need to include stdio.h, and here it says malloc.h, but you can do stdlib.h. Then in the main, you can simply say, let's have a long star buffer. That's always a pointer with the requested type that you want. You want an array of long, so you need to say long star. Then you say the buffer should be equal to cast to long star. Similar to malloc, you need to always cast the return value of calloc to whatever you want. Then you call calloc, and then here you want 40 of these. So first you specify how many items you want, and then specify the type. Whatever the size is, size of a long. Right? If the return value is null, that means you cannot allocate memory. So that's basically an error message that you'll see. But if the return value, which is the buffer, is not null, then you print out allocated 40 long integers successfully and do whatever you want to do with the buffer. Yeah. This example doesn't want to do anything, it just wants to free it at the end. Free, which I wanted to talk about it later, is a simple function like this. The name of it is free, and the input parameter is a void star. So you can basically pass anything you want to the free. Any pointer would be a legal input parameter for free. What does it do? It basically frees or deallocates the space that we have allocated for buffer using either calloc in this example, or malloc, or realloc in the other example, which I'll show you later. So the free is super easy to use. All you need to do is pass the pointer to the beginning of a storage that you want to deallocate or free, and it's going to free it for you, right? And as you see, we don't care about the return value. It has no return value, so the free, basically you just write free and that's it, right? You don't want to set the return value to anything because free doesn't need to return anything, right? All right. Now let's talk about realloc, which is another version of malloc. So far we have seen malloc, calloc, and we saw an example of free. Now, what is realloc? Realloc reallocates memory blocks. Right? So calloc means clear and clear and alloc. Realloc means reallocate. Reallocates memory block. How does it work? If you want to use realloc, you need to have you need a call to malloc before that, or you need a call to calloc before that, or you need to have a call to realloc before that. So the realloc needs the return value of a malloc, a calloc, or a realloc. So you cannot call realloc at the very beginning of your program because it needs a return value from a malloc or a calloc or a realloc before itself. This is the signature. It returns a void star, just like malloc and calloc. It gets two input parameters. First, it's a void star, which is going to be the return value to or return value of. It's a return value of a previous call to malloc, or a previous call to calloc, or a previous call to realloc. And you're going to pass a new size. What does realloc do? It will change the size of that block for you. So let's say the previous block that these have returned has 200 bytes. If you want to change the size from 200 to 400, you just set this to 400 and say update the size, right? That means what? That means grow it. Right? Or if you want to shrink it, you can just say, instead of 200, just say 100. Right? So it's going to change the size for you. If it cannot change the size because let's say you have low memory and you want to grow the size to a unreasonable value, then the return value of realloc would be null. Just like malloc and calloc, which return null when they are not successful, realloc also return null if it cannot reallocate the space that you're requesting. So let's write a program, or let's look at the program that allocates a block of memory for buffer and then uses msize, which I'll tell you what it is, to display the size of that block. Then it uses realloc, the function I'm going to show you in this slide, to expand the amount of memory used by buffer, and then calls msize again to display the new amount of memory allocated to buffer. So in this example, I'm going to show you how realloc is going to expand the size, and also what does underline msize do. These are the include operations. I'm going to include stdlib, stdio, and malloc.h. I will use two pointers. One is called buff, one is called old buff. You may say, why do you use old buff? Old buffer is a placeholder for the initial value of buffer. We'll use that to store the initial or original value of buffer before doing the realloc. That's necessary because if the realloc fails, you're losing the initial buffer. And then I have a size t size to store the size. The first thing we're going to do is we're going to call malloc to allocate a block of memory for 1000 long integers, which is equal to 8000, right? If the long is 8 bytes, that would be 8000, or to be short, 8 kilobytes. So I'm going to allocate 8 kilobytes, and I'm going to cast it to a long, and I'm going to set it equal to the buffer. If the buffer is null, I will be furious and get out of the program with exit 1. That's called handling an error in panic mode. You panic and say exit 1. You don't want to continue because the initial malloc failed. Then you're going to use underline msize function, which gets the pointer to a block in the heap and returns the size of it in bytes. So this is going to return 8,000. We'll see the output. I mean, you can see the output. While I'm writing, showing you this, you can try it yourself. Open your computer and type all of this. I know it's not an easy thing to do, right? But you can manage it. You can take a snapshot of this and then do it offline. And then we are going to print size of block after malloc of 1,000 longs is whatever the size is. And then, by the way, the underline S in the print is the secure version of it. You don't want to be worried about that. That's a special API that you don't need to know. But let's talk about the rest of it. So after you allocate 8,000 or 8 kilobytes, it's time to reallocate and make it bigger. I'm gonna grow the size. Let's store buffer in the old buffer so that if the realloc fails, I don't lose the old buffer. Then I'm gonna call realloc with the existing buffer as the first parameter, and size, which is 8,000 plus another 8,000. This is to double the buffer size. 8,000 plus 8,000 would be 16,000 or 16K. So I will pass 16K or 16,000 to the realloc function's second input parameter and see the result. If the result is null, that means I couldn't grow the size of the initial buffer, so I'm gonna free the old buffer and exit one. Exit one means, I didn't like how the return value was, I couldn't grow the size, so I will exit immediately. But if the realloc doesn't return null, so buffer would be pointing to a longer buffer of size 16 kilobyte. I will call msize again to get the size of the buffer, and I will use printf, forget about the underline s, to print out the size of block after reallocating. And then you can free it at the end, and then exit 0. Exit 0 means there was no error. So that's pretty much how realloc looks like. Any questions? Remember the following. The realloc function changes the size of an allocated memory block. The memblock argument points to the beginning of the memory block that you want to change its size. If the memblock is null, remember what memblock was? The first parameter of realloc function. If the first parameter is null, then realloc behaves the same exact way as malloc. So if you want to imitate the behavior of malloc using realloc, pass null as the first parameter. If the memblock is not null, then it should basically the first parameter should be a pointer returned by a previous call to calloc, malloc, or realloc. I talked about all of that. And if there's not enough available memory to expand the block to the given size, then the original block is left unchanged and the null is returned. So that's how things will look.